Okay, so first of all, ik spreek Nederlands and I speak English. So if you want to have your questions in Nederlands and I can answer in English, so that the people who, and I'll repeat the question and everything. So we can have that talk. Bonus points. Who's the guy whose picture's on the screen now? Who knows who that is? Come on, bonus points. Google image search. Good guess, but it's not Turing. Any other guesses? Who? Deep. Isn't that like a new age guru? Yeah. Dude, you might be in the wrong conference. So, okay, wow, okay, you gotta tell me about that. Didn't know that. Yeah. Very good. Everybody go talk to that guy. What's your name? Ate. PhD physics. We need to talk to that guy.
Because I think he's one of the smartest guys ever lived.
I agree with you.
He disappeared in Naples.
He disappeared in Naples. So our story starts with a little bit of a mystery. He's one of the smartest guys ever, and he was the chosen student of Fermi. And when he was working with Fermi, he was working on principles of quantum mechanics, and some of the things that he's working on are still mysteries for us today. So that's kind of where we start, because some of the work that he started doing is still like a basis for topological quantum computing. And for ages at the TU Delft, they were looking for the famous Majorana particle. So if you get bored or you're kind of curious tonight, let's end this story with where it started. Start looking about Mr. Majorana. So you might be wondering, why is KPN here talking about anything with Majorana or whatever? It's because of my interest for long-term preservation of security and privacy for our customers and their data. Because the KPN CISO mission is to keep, KPN reliable, secure, but also trusted by customers, partners, and ultimately by the whole of Dutch society. If we want to do that for longer than 10 years, you got to know quantum mechanics. So let's talk about why that is so. What's the problem? We're going to dissect the problem a little bit, and then we're also going to talk about, what we're going to do about it. So we're going to take a look at, okay, let's explain the plan that we have, and about why actually all information security people, because that's what I am, and I'm hoping that's what all of you are, other than Deepak Chopra guy, we need to talk. But that we're all, from an information security community point of view, also interested in this topic. And if you're doing anything for a company that is related to risk management or information security, you should know some of this information already. Okay, that's why we're doing this today. So the threat is actually quite subversive. And it's fundamentally that intelligence agencies have complete information awareness. They've had this for some time. They know everything there is to know about us. They can create an entire digital dossier. They know where we are. They know who we talk to. They know how we communicate. And they know who those confederates are, or groups of people that we hang out with and communicate with online. And, it's really weird, because despite this overwhelming capacity to have a sort of Eye of Sauron view over everything that's happening, they're still worried about pockets that they can't penetrate. And they refer to this as the going dark problem. Because the light, the Eye of Sauron, goes dark when people are using things called cryptography or cryptographic tools. And actually what we see is that, instead of trying to keep that practice in play and keep privacy and this type of mechanism to prevent foreign intelligence agencies from reading our communication, instead of keeping it strong, we're actually looking at weakening it or killing it. So even though that we had Edward Snowden revealing all the capacity and the powers of intelligence agency, how many of you have seen a massive global uprising against them? How many of you changed your behavior and suddenly began encrypting everything? Yeah, one guy in the pink shirt. And I would say the next thing we need to get him for Christmas is a tinfoil hat. Really? Did we really? No?
Did it before that.
Ah, okay. All right. Well, that's not then really correlated, but okay. Thank you for trying. So the idea is we don't have an enormous amount of informed public opinion that actually wants to do something about this capability from intelligence agencies. So what we actually see is that intelligence agencies are trying to renew a war that they once fought in the 1990s. They're trying to renew the crypto wars. We're going to talk about that in a minute. And we also know that the NSA has actual budgets. It's called a black budget because they don't have to disclose any of the information to Congress. But part of the black budget program is the program Penetrating Hard Targets and Owning the Net. In Penetrating Hard Targets, they actually talk about how are we going to kill this crypto thing, especially when it's good crypto. So how do we get around it? Well, maybe what we need to do is develop a quantum computer that can break some of that good crypto. The other thing that we want to do is own the net. We want to have an ability to have offensive security programs in place where we can bypass the cryptography altogether by getting in one of the foundational areas, because good crypto built on top of bad protocols, bad software, bad hardware is bad crypto. Yeah, it has no chance in hell of succeeding if the underlying foundation is weak. So both of these programs are intent of getting the clear text communications that was there before the crypto was applied. Are we all still understanding me? We're all still there. We've had our coffee. We're good? Yes, just checking. Okay, you're going to need it. So the question now comes, and it's coming back, and Theresa May has recently said, you know, maybe we should get at that annoying human rights thing that makes it so difficult for us to do what we need to do as governments and law enforcement agencies. It's basically fully bringing back the original crypto wars. In the Netherlands, we have something called the Kabinetsstandpunt op encryptie. How many of you know that? Like, all right, you definitely know that, yeah, okay. So the Kabinetsstandpunt on encryption basically says, you know, we might do a lot of things in order to help and assist law enforcement in their ability to detect what's happening, but we will not weaken good cryptography. They've said that, they've made it very clear. They've embedded it as a sort of national standpoint. The clue is that although this is a great move, I have to ask myself what will happen when the threat becomes very close. And you're seeing some of that happen in the UK right now. So the original, let's see, is this the laser pointer? Okay, no, I don't know where the laser pointer is. But when you see the guy to the lower left-hand side of the slide, that's Louis Freeh. Louis Freeh has a rather distinguished career as the former head of the FBI. And as the former head of the FBI, you know, the things that he wrote his book about is he brought down the mafia, he investigated Bill Clinton, if you'll remember that famous blue dress with the stain on it, yeah, and he fought the war on terror. Okay, this was the CV of Louis Freeh, and Louis Freeh was very much a sponsor of breaking into cryptography and not allowing strong cryptography to be used by the public. In the original crypto wars, the good stuff was reserved for use by the United States and its agencies and its consumers. Only the crappy crypto was allowed to be sold for export grade. So outside of the US, you would only get the crappy stuff, which meant that it was subject to foreign surveillance and intelligence gathering. It's a weird game. The next guy, everybody knows the next guy coming from the left? Who's the next guy? Comey. I miss Comey, don't you? So Comey was also one of the primary proponents for actually asking for a weakening of crypto. If you remember the FBI case against Apple, remember, he wanted to find a way to get past the device encryption on the iPhone of the San Bernardino victim. So, you know, they all want the same thing. How do we get to the clear communications? Theresa May takes it way too far, but they actually want all of these things. They want, instead of, you know, what they call a back door to get into the crypto, they want something called a front door. And the only difference is it's the same thing technically, except the front door has been approved by a judge. Yeah, and they then want to say, all right, we don't just want this back door or front door, we also want something called golden key management, which means we can split the encryption key across various parties. In order for this to work, in order to trust, like let's say I have an encryption key here and I'm going to give a little bit to every part of the room. How long do you think it's going to take before bits of that leak? How long do you think it's going to take before that process breaks? Now imagine that I do that, but I do it across 160 countries on planet Earth. Because once I have a back door for the United States with split key management, I also have to give it to the Russians and the Chinese. Everywhere where there's a geography for these tech industries, they will all want to have this. This requires excellent technical execution and flawless process implementation. I want to ask you if that's a good job for big government. It's a zero tolerance for screw up. So the idea is that in order for this to happen, it requires a certain amount of magical thinking, because this cannot happen in the real world. We will not get this working. And so it actually brings us to the thing about, okay, well, what does quantum then have to do with this? So we know we have this, real issue with getting past encryption, and we don't know whether we should kill it altogether or break it. Well, how does quantum enter? Well, quantum enters actually in pretty much after 1900, because before that we were really very much dealing with classical physics, and there are some, factors. You need to talk to Ata at the end if you want to know more than a couple of these slides. But the idea is we're going to describe the macroscopic world. We're going to talk about, very deterministic. So I do this, and then this happens, and we can pretty much predict that because it's intuitive. When we look at quantum physics, we're looking at stuff that happens after 1900. Really, the birth of quantum mechanics and quantum physics is pretty much the Solvay conference in 1928, when you had Einstein and Bohr having heated discussions with each other, trying to figure out what this really meant and how this would be reconciled with classical physics. It explains the microscopic world. We're talking about very small subatomic interactions. It's probabilistic, which means if I do this, I have a probability that this may happen, but I don't know for sure. This could happen or that could happen. And then there's a very strong central role of the observer. It is absolutely not intuitive. This means for us, for information security, that we're very concerned in understanding these things because it's about both offensive and defensive measures. From the offensive side, we want to understand when will the post-quantum era arrive, or the era where we actually have a quantum computer. If we have a quantum computer, any moment after that is called post-quantum. And that means we'll have to have new strategies of how we do cryptography. So let's talk about what a quantum computer is for a moment. Let's look at a couple of properties of quantum computers. So a regular computer deals in bits. Yeah, it's a 0 or a 1. We all know bits. We all know binary. We understand that. But a quantum computer actually deals with qubits. It can be a 0 and a 1, and this is the part that blows my mind, which you already need to have had your coffee for. It can be a 0 and a 1 at the same time. So if that doesn't blow your mind, nothing else will, because that, so it can be a 0 and 1 at the same time, which already means that in the same space where you had the 0 or the 1, you have the 0 and the 1. Now imagine that we have this other property that we add to it called entanglement, which we can actually entangle those qubits, which is the 0 or the 1, to another 0 or a 1 at the same time. Yeah? And now that this property is going to give the quantum computer scale. So we're suddenly in the place where we had a 0 or a 1. If we entangle 2 qubits, we're going to have a 0 and a 1 and a 0 and a 1. If we entangle 4 qubits, we have a 0 and a 1, a 0 and a 1, a 0 and a 1, a 0 and 1. Do you get the idea about scale? So in the same spot where we were, with Moore's law doing this, we're now suddenly doing exponential curves. We're going all the way up because we just increased the amount of potential computing power we have at our disposal. Okay, so entanglement is also really funky. It means that when we entangle these things together, these two photons together, that we actually cancel the other one out. So if we have a +1 on the one side, we'll have a -1 on the other side where the end result is 0. But they're so interconnected with each other that actually affecting one, regardless of distance, regardless of whether it's, two chairs away or 2 universes away, which is not really possible, but regardless of distance, we have this property of entanglement. Again, mind-blowing stuff which requires coffee. So, are we still with me? Are we still with me? Yeah? Okay. All right. Einstein didn't like the property of entanglement. He said, it's not possible. What is this nonsense about across the universe you have this thing? That would mean that there would have to be a mechanism for these two things to interact faster than the speed of light. That's impossible. So he called it spooky action at a distance. Yeah, he said it couldn't work. But what we saw actually is there's a test. It's called Bell's inequality, and testing of Bell's theorem requires us to actually look if this is still possible. And what they did at the TU Delft is a loophole-free Bell test, because every time we tried to test entanglement, we had to have loopholes to explain what was happening. And the first time they did it loophole-free, without having to have all these other, well, this happened, but, you know, we can explain it with this, was when they published this only a year and a half ago in Nature at the TU Delft. It's something to be very proud of, I think. So other properties of quantum is that, you know, especially with a quantum computer, we have certain properties that, like, if you try to observe or, you know, have some noise, that they're very finicky. These quantum states are so finicky, in fact, that they will collapse if there's the introduction of noise or observation. And that means that you can't copy or eavesdrop the communication. Lawful intercept, anyone? Yeah, you can't do it when you're dealing with these links that are protected with these properties. So you should know, though, you know, even though we're all talking about quantum computers, that there's more than one kind of quantum computer. And the ones that you might have seen or read about in the news, like D-Wave, that's called a quantum annealer. It's set up to do particular types of problems and properties, but it's not the wonderful thing that, you know, the holy grail that like the quantum scientists are looking for, which is a universal quantum computer. So that's really what we're all going after, because it will require physical qubits. It won't have a supercomputer next to it compensating for all these logical qubits. It'll be able to do these problems by itself. It's the granddaddy. It's the big, you know, X Prize challenge-y thing. Okay? And we really want a universal quantum computer because it can solve a whole bunch of really cool scientific problems, like how to treat cancer better, how to make more tailored drugs, how to do scientific modeling and protein folding and nitrogen fixing. I mean, it can do very, very nice scientific simulations. We need this type of, you know, machine to do those problems, but it can also do other stuff. And what does that mean? What's the other stuff it can do? Well, you know, we talked about Moore's law, right? Moore's law is every 18 months we have a doubling of our computer power. Everybody know Moore's law, right? I'm looking at you. Well, the clue is that Moore's law at a certain moment actually, instead of having this linear expansion, actually begins to decline. And then we have something called Amdahl's law, which means we can keep adding processors to the mix, but we won't keep seeing this linear increase. We're going to actually see it slope off. And when this happens, we don't have additional processing power at our disposal anymore. We don't have that beautiful property of Moore's law, so we just need more computing power. And what's really cool about a quantum computer is that, like, before it existed, we already had algorithms that could be used on top of it. How crazy is this? So we already had the stuff that's waiting now for a quantum computer to exist in order for it to be run. And that's Shor's and Grover's. And this has a very strong bearing of cryptography for the following reasons. Cryptography, especially the asymmetric public key cryptography that we use today, is really based on two big, difficult math problems. It's the integer factorization problem and discrete logs. So let's talk about that for a second. Who's kind of awake or who's not awake? Gonna pick on someone. You look so innocent. Yes, you do. The guy who just put his head down and cried almost. Innocent. Yeah. And so who do you work for?
Dear Bytes.
Oh, no, you can't go. All right, who doesn't work for Dear Bytes or KPN? Really? Seriously, guys. I knew something was wrong. Yeah, all right. You don't work for, like, either company that's sponsoring the event. Thank you so much. Okay. So where do you work?
ABF Research.
Oh, you could probably do this problem then. What is 7 times 8?
56.
Good job. What are all the factors that would result in 56?
2 and 7.
There's a few more. Okay, but you get the idea.
Yeah.
Right? I asked him a question, what's this number times multiplied by this number? He said 56, bang. And then I said, okay, what are all the numbers you could multiply together that would get into 56?
And it's 3 times 2 and 7.
Yeah, and a couple of more numbers that would get you to 56, but you get the idea. We keep
Older.
all the factors that would lead to 56. Yeah. So the clue is that computers kind of react the exact same way. They find it difficult to reverse something that we call a one-way function. Doing the function this way, what is this times this, they can do. Doing the function the other way, I have 56, now tell me what all the possible factors could be, they can't do. And this is the basis for why a quantum computer will kill crypto, because it will be able to reverse the one-way function, because it does have the computing power to go bang and tell you what all the factors are. And when we apply Shor's algorithm, we've got it. So you have a piece of encrypted text, and now you can figure out what all the potential, key things were that led to it. Think about how cool that is. All right, guys? The second problem is discrete logarithm problem. And that is basically, when you take a number and you raise it by an exponential value, you get another number, like 2 to the power of 4 is. And when we take the discrete logarithm problem, it's also a one-way function. So if we have this number, to which number did we raise it by an exponential to in order to get that result? The computers have the same problem doing that problem. So 2 difficult math problems are the basis of all of our current crypto. And the quantum computer can solve those difficult math problems. Okay, we all still with me? We've got this? I tried to make the math simple. We're good? Okay. So the clue is that, you can do this. You can break crypto as we know it by ABN AMRO. I'm just kidding. But you can also do all this other cool stuff. So it would be silly to try to curtail or ban or control the developments in quantum computing because of all the other things that it could actually result in. And everyone is trying to do this all over the world. It's a sort of Formula One race about who gets the quantum computer first. And that should be clear, but you should also know that the European Commission have pledged €1 billion to actually helping have a quantum computer and have been able to pluck the advantages of all the different quantum technologies that we have at our disposal for Europe. When's the last time you heard the EU saying they'd do €1 billion for anything else? So it's a really big deal, is what I'm trying to say. And you probably are wondering, so how close are we? Are we there yet? Do we actually have a quantum computer that can actually break all of our crypto? And the answer is no. And that's partially, again, I wish I had a pointer, but it's partially determined on really the size of the keys we use, because the bigger the key size, and size matters, the bigger the key size, the harder it is for a quantum computer to break it, because you need more qubits to be used and more qubits to be available by a quantum computer. We measure quantum computers now by the thousands of qubits they have. There is no quantum computer that we know of now that has more than a couple of hundred qubits. At least not anything near approaching a universal quantum computer. D-Wave has plans for their quantum annealer to go above 2,000 qubits in the near future. That's very interesting, but that's not going to break your crypto. Okay. We all still with me? We understand the idea of size? Keys? Good. Okay, so if you know this is a problem and you work in our field today, what are you going to do about it? Well, the first thing we're going to do, because I just showed you, is we're going to increase the key length of cryptography that we use today. For those of you that have the KPN CISO app, we open sourced all of our security policies for the world, for the benefit of you. So there's also a quantum module that's coming up in the next release. So everything that I'm telling you now, we're actually going to implement in our security policy. We're already going to take steps to be quantum resistant. So know that. But the first step is to increase the type of crypto you use in terms of key lengths, and then the second one is to look for where in your network you're going to use quantum key distribution, the same principles of quantum mechanics, to actually protect your communications. The third thing we're going to do is investigate whether we can do a new algorithm set that isn't subject to the same weaknesses, so that even when there is a quantum computer, it'll still be intact. Sounds pretty cool, right? Okay. Are you leaving because you don't like it? No, I'm just making sure. So, yeah, or he's just calling his friends at the NSA. So the deal is that, as far as key length goes, this is also the advice of the NSA. The NSA actually published a redefinition of how they want to handle Suite B, and they've said, look, as the NSA, we have 2 objectives. One of them is to read everybody's emails. That's called signals intelligence. The other objective is called information assurance. We want to make sure that nobody reads our emails, although we do it regularly thanks to shadow brokers. So they have this dual objective in play. And what they said is, we want everyone who supplies things to us to transition to quantum-resistant algorithms in the not-too-future. So if you use the Advanced Encryption Standard, make sure that you're using AES 256. So if you got encryption, use the biggest key length. Yeah, they've actually published this. This is open source information. The second step that I'd like to encourage you to do, because we get that, right? We can do that right now. We all can take our crypto and we can increase the key length. The second step that we can't do so easily is look at how we can use the properties of quantum mechanics to actually get better security. And that means that when we have a channel between Alice and Bob, and that's usually a fiber channel, that we're going to look for the presence of the eavesdropper, also known as Eve. And how we're going to look for Eve is we're going to see, hey, can we detect someone observing, remember the principles of quantum? Can we detect someone observing or trying to copy information over this link? Because if they're doing that, we'll see them because they'll change our traffic. How it really works is like this. So Alice is trying to send a message to Bob. Basically, she's sending, messages over fiber, over a light channel. And that means that she's got a photon source, also known as a single photon emitter, and she's going to set up polarizers, lenses basically, in a particular direction, with a particular orientation with slits in it. The orientation is very important. She has to communicate this over an offline channel, because if Bob's aren't set up correctly, the message from Alice will never get to Bob. They'll be dropped. And the clue is, you're going to look for Alice, because Alice is going to send something. Bob's going to say, hey, did I get this message from Alice? And when it doesn't work, when he doesn't get what Alice sent, they'll know that Eve was there. Because the message will have been changed by this Heisenberg uncertainty principle, which, you can't measure or observe without altering the communication that's happening between Alice and Bob. And it's just a fundamental principle of quantum mechanics. So they're using this fundamental principle to determine the presence of an eavesdropper. But there are problems, there are limitations, because this is not internet scale. Because you probably don't have dedicated fiber links with everyone you communicate with. How many people do? I do. But no? Okay, so here's the clue. What we want to look at is something called free space quantum key distribution. What we've done in Europe is Paulo Villarese from the University of Genoa has basically put up a quantum channel between Las Palmas and Tenerife, 144 kilometers, so way better than the maximum distance of fiber, which is about 64 kilometers. And he's managed to bounce lasers between these two islands, even with the water vapor and all the signal distortion and everything. He still managed to set up a quantum key distribution link between these two areas that actually resulted in a full secure channel for quantum. The scary thing, though, is that's as far as Europe got. What's really cool about the Chinese is the Chinese are building a 2,000 kilometer long quantum transmission network from Shanghai to Beijing. They've also launched the world's first quantum communications satellite, which is also capable of, outside of this dedicated fiber infrastructure, of communicating, for example, to equipment on the back of a tank. And the reason that they've said they did this is, in the event of a regional war, we want to know that we have a secure communications channel. But look, tell me why you need a satellite for that. What do they know that we don't know? Why are they so better prepared than we are? They spend the most amount of money in all quantum technologies. It's actually written in their 5-year plan. So they spend the most amount of money and they produce the least amount of openly disclosed research. There is no research you can find. There's a lot of academic institutions involved. Nothing is published. They attend all the conferences. We don't hear anything from their scientists. And they have the biggest budgets of us all. So what do they know that we all don't know? Could I just save that for just a few seconds? You probably are going to tell me what they know that we don't know. That's
Our universities,
sorry.
they know everything because they are in our universities.
Okay, thank you for that slightly ethnically questionable comment. Yay. All right, I'm just kidding. I need to get my kicks from somewhere. All right. So, what we're also working on is we're working on that new algorithm set, right? So we have 3 options, remember? We've got, the first option was to look at how we actually fix what we've got now, which is just increase key length. Second option is look for places where we can do quantum key distribution. Third option is that new algorithms. And the new algorithms are called post-quantum cryptography. This sounds hard, but it's not so hard. What you should know is we've actually had post-quantum cryptographically resistant algorithms since 1978. The first of which is called Mecalese. It's based on lattice-based cryptography. How many cryptographers are out here? Okay. That is a shame because we need, so for those of you that are thinking about entering the field, all I can say is your future is bright. We need more cryptographers. But the idea is that lattice-based cryptography has been around for a while, and the biggest trade-off here is both processing power and bandwidth. Because in order to actually do good crypto, it shouldn't cripple your links that you're sitting on, so your internet bandwidth can't be consumed by this overhead of crypto on top of your regular traffic. Think about it. If I encrypt everything, what do I need it to be? I need it to work on a smartphone, I need it to work on small processors, I need it to work on the Raspberry Pi, but I also need it to not eat up all my bandwidth, and consume all my traffic while just trying to get my signal out. Because everything will be ridiculously slow. So we have these trade-offs, and what we need to find is a solution that actually provides us, and one of the algorithms is actually called A New Hope, a solution that provides us this good balance between security and basic communication. And the candidates that we have for that are, one of them is called SIDH, or Super Singular Isogeny Diffie-Hellman. Say it 3 times fast. In the cryptographic community, isogenies are not very well understood. It's not widely embraced, but Phil Zimmerman, who is like a BFF, says it's the hardest thing that we have. I believe him. The fundamental thing you need to remember, though, is it's not about later. It's not about, well, I don't have a strategy for quantum, but I'll wait 5 years. When the computer arrives, then I'll figure it out. My company doesn't really affect us, so whatever. So this is not a good attitude, because the clue is this. Everything you have ever done, or put online, everything that even you've done encrypted and put online, everything that anyone has ever done on behalf of you and has encrypted or put online is at risk. Because the principle of the majority of these governments and intelligence agencies is capture it now and decrypt it later. And old secrets here are just as good as new ones. Think about again why I told you that KPN is even involved in this area. It's because of the preservation of long-term secrecy and privacy. We're not here for 5 years. KPN is one of the oldest companies in the Netherlands. We want to be around for another 150 years. That means our customer data needs to be protected for pretty much that lifetime. If we want to do things like that, that means we need to have a forward-facing strategy that thinks beyond this. And that means the gemeentelijke basisadministratie, or what's that in English? I don't know. The municipality information, or your tax information, or that. We want that to be secret for at least the next 40 years. Right? Don't you? So that means we've got to fix this now, before the quantum computer gets here, because then we'll be too late already. KPN did one thing. We did one thing and we did it well. On one of our fiber channels, we basically, between The Hague and Rotterdam, set up a quantum link. We wanted to figure out how easy it was, whether we could actually tolerate it on fiber, whether there would be signal attenuation, dB loss. All of these things went very well. It was able to be set up relatively early, and now here's the crux. You need to figure out where you're going to implement this on your network, because again, you can't do it everywhere. If you do free space quantum, you need to differentiate, like, what are the use cases for that? Free space quantum, like, am I going to ride it in the back of a truck? We're certainly not going to put it on top of, the de ravenbestuurders, like mobile wagons. You really have to have a very clear use case, is what I'm saying, before you start playing with this technology. And you need to be able to identify the key points in your network where it's really required. So inclusion here, we're not ready at all. We're just getting started. You know, we're trying to figure out what we do with our requirements for our policies. We're trying to figure out what we do with our quantum links. And then we also need to figure out a new way forward with algorithms that need to be tested so we can fail early. The good news is that IBM has a publicly available quantum computer where you, all of you now, today, right now, as you're sitting here, go on 4G and get an account. It has 20 qubits for you to play with. All the intellectual property belongs to IBM, but you have 20 qubits, which you can play with. And you can say later, I had an account on one of the first quantum computers. Okay, and be very cool. Google has already announced they're going to do a quantum supremacy experiment where they introduce 50 qubits. They announced this last year in about June, and it's roughly a year later. And I haven't seen it, but Google actually has 2 plays for a quantum computer. So they're working on their own quantum computer, and they bought one from D-Wave just to play with. So what we need when we see these kinds of developments, and it's only expanding, is we need a common way forward. So when I wrote the slide, initially IBM only had 5 qubits for you to play with. And in less than a year, they came from 5 to 20. This is an exponential growth area. It is only going to get bigger, badder, meaner, and more in your face. You need to figure out what to do now. Again, I'm asking you, what is your quantum strategy? How are you going to solve this problem? And you have a responsibility towards your company, your customers, and your data, because your data wants to be free. And if you want to really help that, then you have to do this now. So take a look. You know, I think one thing that we need to do when we have this common way forward is not forget what we always did in information security. We always need to do defense in depth. So it's about combining multiple measures and looking for optimal balances and the right trade-offs between security and usability. So I wish you a lot of luck. Thank you for being so awake. I don't see too many sleepers. Yay! Well done. And if you have any questions, I'll be more than happy to answer them.